once more. So here's where things start getting a little bit more interesting. Sweetness doesn't always mean easy. But yeah, I think it'll be kind of cool. Then again, I suppose you will be the judge of this at the end. All right, but here's the deal. If you recall from our discussions of aldehyde and ketone chemistry, you may remember that it is completely doable to react an alcohol with either an aldehyde or ketone. And if you employ just a catalytic amount of acid, you can actually end up making an acetol as well as a hemiacetal derivative out of that ketone. And if you really think about it, your sugars are basically aldehydes and a bunch of alcohol all in one molecule. So what you have to consider then is the fact that when you look at your aldehyde position, position 1, if you start counting the atoms to the different hydroxyls, there's actually a few options that look like potential, decent ring sizes that you could make. So for instance, the numbering that I'm showing right here, 1, 2, 3, 4, 5, all the way down to the penultimate carbon, I make a right towards that penultimate oxygen, and all of a sudden I'm looking at a potential 6-member ring, which seems like that would be perfect for this molecule to react with itself and form a hemiacetal with those two fragments. I'm also showing a few other you know alternate pathways, right? If we went all the way from carbons 1 through 6, well, then the next oxygen will be position 7, so that will be a 7-member ring, which is not as ideal. On the other hand, if we stop at position 4 and move over to that corresponding hydroxyl oxygen, that will give us a 5-member ring, which is actually not a bad alternative. 5 and 6-member rings, good stuff. Higher than that, not so good. Lower than that, not so good either. So we're going to consider that, and you probably already saw this. This particular sugar that I picked for the example is D-talose. D because the penultimate hydroxyl is pointing to the right, and then talose because of the sequence of the rest of the hydroxyls in that hexaaldose. Okay, so now one last thing that I'm going to mention to you, because this is going to play a role into whether we make the 5-member ring or the 6-member ring, and spoiler alert, we're going to make both. To differentiate them from one another, because technically they're both talose at the end of the day, but the structural features are going to be different. So to address that, we're going to rely on spelling out whether it's a 5-member ring or a 6-member ring that we're forming. And for that, we use the name of furan, which is this 5-member ring molecule, this oxyrane molecule with 2 double bonds, as well as pyran, which is the 6-member ring derivative. These are not sugars, but that's the shape that you form, and those are the names of those shapes. So we're going to incorporate them into the ultimate name right here. All right, so we're going to first focus on the 6-member ring. So if we go from carbons 1 all the way to carbon 5 and then make a right turn to oxygen, the direct oxygen, the penultimate oxygen, that will give us 6 atoms. So here's the way that this works out. Most textbooks, in my opinion, they don't mess this up, but they don't give you proper perspective. So when you get to this ring structure, it becomes kind of like a daunting, jump. Having to go from the simplistic, Fisher projection to the actual ring structure. So what I recommend that you do is that you take that Fisher projection and literally pretend that you are pushing it. Push it to the right so that the aldehyde ends up all the way to the right of the molecule. So kind of like you're pushing it and it's falling flat on its face, flat on that aldehyde face of it. you know so it falls flat, and then notice what's happened. All the hydroxyls that used to be on the left side of the Fisher projection are now pointing up, and all the hydroxyls that were pointing to the right portion of the Fisher projection are now pointing down. All right, now as far as the numbering goes, this is still the same as before, right? This is carbon 1, 2, 3, 4, 5, 6. And what we're trying to do is have oxygen, the penultimate oxygen, be the alcohol that attacks the aldehyde. That's what's going to give us a six-member ring. So before we can do anything else, we need to ensure that this hydroxyl, the penultimate hydroxyl, ends up in the horizontal position, because we're going to try to wrap this around like a ring. You'll see in a second what I mean exactly. But in order to ensure that this works out correctly, this OH and the penultimate carbon has to be on the horizontal position. So the way you treat this is you simply say, yeah, right now we have a linear rope. So the way you think about this is that this is technically, a, a single bond, single bond, single bond, and they're all free to rotate. So you could say, all right, well, so if we rotate this this three-member fragment about carbon 5, basically what we'll have to do is rotate the hydroxyl clockwise towards the horizontal position. That in and of itself will mean that the CH2OH will have to rotate clockwise towards the hydrogen position, and then the hydrogen will have to rotate clockwise towards the OH position. So ultimately, what you would do is redraw that, fallen view of the Fisher projection, and then acknowledge that, yes, okay, now hydroxyl is going to be on the horizontal position, right? CH2OH will now have to be above, and then the H that was above now is going to be pointing below, because we did the full rotation for all three of those groups consistently. All of them rotated clockwise, and that's kind of the point. And when you have all the atoms involved to make the ring in the horizontal position, technically what we do is we take this linear rope and we just wrap it around to form a ring. So here's where we draw what is known as the Haworth projection. And since this is going to be a six-member ring, technically this is a pyranose ring, or the pyranose derivative, right? Kind of emphasizing that, we're deriving this um, from pyran, or the structure of pyran. All right, so what you do is you say, okay, 6 carbons, well, technically 5 carbons and 1 oxygen in that chain are going to lead to a 6-carbon chain. And you basically draw this semi 2D picture of it, right? So just like hexagon. And notice that I'm putting the oxygen here on the upper right corner, which is usually by consensus the place where the oxygen, gets drawn out. Now in the Haworth projection, what's then done is that the two positions that stick out of the ring are simply drawn as a vertical line, right? So one pointing above the ring, one pointing below the ring. And that's true for all the positions aside from the oxygen, because the oxygen doesn't have any additional bonds aside from the ones making up the ring. All right, so here's the way it works. When you make this six-member ring, what you have to recognize is that this oxygen in the ring is position 6. That's the oxygen at the tail end of that horizontal line. And the consensus is that you pretty much move around the ring clockwise, right? So if this is position 6, which is literally the last position of the chain, then going clockwise is going to take me straight back to position 1. And you might think that's kind of a little weird, but you have to remember position 6, or oxygen 6, is wrapping around like this ring to attack the aldehyde carbon and form an acetal, actual functionality, if you want to call it that. So going clockwise from 6, we go back to 1, then 2, then 3, then 4, then 5. And here's how you basically approach it. You look at this, fallen Fisher projection, and whatever is pointing up will remain pointing up. So position 2, and here be very careful, position 2 has hydroxyl pointing up. So at position 2 and position 2 only, the hydroxyl is going to be pointing up. So here I'm not color coding everything so you can see where everything is. Position 2 is in green, position 3 is in pink, position 4 is in blue, and position 5 is in red. So position 2 we have a hydroxyl pointing up, H pointing down. Notice that I'm skipping position 1 for the moment. I'll tell you why that is the case in just a second, but for now just go with me. Position 2 is where we start. At position 3 we also have a hydroxyl pointing up, so position 3 hydroxyl will be up, H will be down. At position 4 we'll have hydroxyl pointing up, H pointing down, so this is exactly what we draw at position 4, hydroxyl up, H down. And at position 5, what points up is not hydroxyl, rather what we have at position 5 is CH2OH. And below we have H. So that's literally what we draw here, CH2OH pointing up at position 5 and H pointing down at position 5. Okay, and this takes care of the backbone of talose. Now, position 1 is interesting because if you kind of think about it, before what we had was an aldehyde, right? That's an sp2 hybridized carbon. It's trigonal planar. But when the alcohol at position 6 attacks, that sp2 hybridized carbon becomes sp3 hybridized, and what used to be an aldehyde will ultimately become an alcohol, right? So in essence, we're making an hemiacetal. But this aldehyde, by the mere notion of it being an aldehyde, means that we also have at position 1 a hydrogen directly attached to it. So what we're going to have here in the Haworth projection is hydrogen and OH ultimately. So you could draw one instance where the OH points down and the H points up. And this is only one out of two possibilities because the aldehyde has no preference as to whether the alcohol attacks from its top hemisphere or if it attacks from the bottom hemisphere. So this one will be the situation where the hydroxyl attack from the top hemisphere. Okay, so now this has a particular denomination. When the hydroxyl at position 1 is pointing down, we call this the alpha anomer. And we are referring to that with a very peculiar name, anomer, because that's the only position in the ring that's truly a hemiacetal position. Everything else in the ring is just alcohol, alcohol, alcohol. Or if you want to be, not as technical, every other position aside from position 1 is just a carbohydrate, right? But this is truly a hemiacetal. You have the OH, and on the same carbon, you have an ether linkage, right? So that's literally your hemiacetal. But as I mentioned before, that nothing stops this reaction from um, ending up attacking from the bottom hemisphere and having the hydroxyl pointing up. And if that's the case, if the hydroxyl at position 1 points up, we call this the beta anomer. So as far as differentiating the two molecules name-wise from each other, there's a couple things we say. First of all, because the CH2OH fragment at the penultimate carbon is pointing up, these two things are D sugars. Now, the one here on the left is not only a D sugar, but it's the alpha anomer. So we will say D hyphen alpha. And then you could say talose, but talose will not tell you whether this is a 6-member ring or a 5-member ring. So in addition to that, you kind of break the word talose by inserting the word pyran in between. So then this is ultimately I'm sorry, D alpha talopyranose. And this tells you everything. It tells you that you're dealing with the alpha anomer. It tells you that this is the D sugar, meaning that the CH2OH, the penultimate carbon is pointing up. And it tells you that this is the 6-member ring. So that name has everything in it. This is as specific as you can get about the structure of the molecule. And you may have guessed it. For the other version, the other epimer, we basically have D beta talopyranose. And same idea. This tells you that the sugar is got its CH2OH at the penultimate carbon pointing up. It tells you that the anomer has the hydroxyl pointing also up at carbon 1 and is the 6-member ring. So you have that whole picture right here. All right, so I'm going to finish this part by showing you the 5-member ring sugar that you can also generate, because you may recall by looking at the Fisher projection, you could stop at carbon 4 and then make a left turn onto its direct oxygen, and that will give you 5 second row elements making up a ring, and that's totally allowed. Now, a 5-member ring is going to be referred to as furan, so that will play a role in the final ending of the name. So what we're going to do here is the same as before. We simply push this molecule to the right, make it fall flat on its face. You label this from carbons 1 through 4. And here, just like before, we want the hydroxyl at position 4 to be pointing in the horizontal position. So the way to do this will be to rotate this counterclockwise. So rotate this counterclockwise towards this red segment. The red segment will have to rotate down towards where the hydrogen currently is, and then the hydrogen will have to rotate counterclockwise towards the OH. So what will end up happening for this rope, this linear rope, is that we will end up with OH pointing in the horizontal position, which is exactly what we want to happen. We'll have the H, which is going counterclockwise, basically displacing the OH. Now that's pointing up. And then this whole red segment is now pointing down. And I'm drawing it just with the proper chirality so that, you have a better sense of what's going on, right? But it's still that red segment pointing down as a result of all of those three groups rotating counterclockwise. And once this hydroxyl is pointing in the horizontal direction, that's when we wrap it up and make the ring. And this is going to be now a 5-member ring. So although I did put the oxygen on the upper right corner, this time I'm going to place it on the upper left, mostly because this bulky chiral group is a little bit difficult to point and draw, on the back side of the molecule. All right, so I'm going to put the oxygen here on the upper left. But we're still going to go clockwise about this ring. So this is position 5. And going clockwise will take me from position 5 back to position 1. So this is position 1, 2, 3, and 4. And ignoring position 1 for a second, we simply copy what happened at position 2, position 3, and position 4. And namely, positions 2 and 3 have the hydroxyl pointing up. So we're going to do that. Position 2, hydroxyl is pointing up. Position 3, hydroxyl is pointing up. And at position 4, we'll have the big chiral moiety pointing down, right? So that's basically what I'm reproducing here at position 4. All right, and then that brings me to the alpha, well, technically the position 1, the carbon, what used to be the carbonyl position. On the one hand, we'll end up with OHH, such that the OH is pointing down, in which case we're dealing with the alpha anomer. On the other hand, we'll have the situation where the OH points up, in which case we have the beta anomer. And as far as naming this, it's still talose, it's still a D sugar. Now this is a little bit tricky because this thing is pointing down. So it might be a little bit tricky to kind of go back and forth, but if you go from the Fischer projection to the ring, and you should remember you started with the D sugar, so this is still going to be a D sugar. That's not changing. But now we have the alpha talofuranose, and we're saying furanose to emphasize that this is the 5-member ring version of talose, whereas the second option right here, the beta anomer, will say that this is the beta talofuranose to emphasize that this is the 5-member ring sugar of talose, but it has the beta anomer configuration at position 1. Okay, so with that, I think we cover a good length on this video alone. So in the next video, I'm going to show you pretty much the same thing, but in application to the ketose sugars. So you'll see more of the same, and then some things different, as it usually is with the sugars. So catch you in the next video. Bye bye.